that instructions is there, take your cursor over there. And these are the instructions going to appear. So whatever is actually instructed, just follow those things and then you have to proceed, right? For example, L1, L7. So L1, L7 we have to connect. L1 is the channel 1, L7 is the sine wave. So we are going to connect this first of all, right? Next one is L3, L7, L4, L5. So L3, L7, L4, this is L4, diode output and the resistance 1 terminal, L4, L5. Then L5, L8, L12, L6. L5, L8, output of the oscilloscope, the output of RL. L5, L8, L12, L6. So this is your L12 and this is your L6. L8, L9. Then L8, L9. So where is 9? So yeah, channel 2 is 9. So yes, oscilloscope is connected to channel 2. So now what you have to do? First of all, you have to check the connections. Whatever we have done yesterday, the similar thing we are going to follow today. So check the connections, click on this, check the connections. It is showing right connections, set the load resistance. So you can see on the screen, it is going to show that your connections are correct. And now you can set for the resistance. So now set the resistance by dragging it. When you are going to drag, just click OK. Blue button will come at RL and I am going to drag it to 1 kilo. That's the maximum. So now you can see this is 1 kilo. This is coming 1 kilo over here. Right? What do you have to do next? Next you have to click on. Make it on. Whenever you are going to make it on, the sine wave button becomes active. So now click on the sine wave. Once you are clicking on the sine wave, your oscilloscope becomes active. So click on the oscilloscope. And now you are so this is the output available. Now in the similar way, this is and this is the channel 2. So channel 1 is the input, blue line, and channel 2 is the output. If I want both of these all together, click on dual twice. And this is what red and blue, both of the inputs and outputs are all together. And this is what you will be having. Correct? So in the similar fashion, just you can change it. You can make it in this way, drag the channel 1 Y position or maybe the voltage per division, and it is going to give you some such type of thing. So I'm dragging the Y position. Dragging the Y position can give me the clear picture that how the output is actually looking like. So this is half wave rectifier. I hope many of you have followed me. So can you please help me to figure out that how many of you have been following whatever we are doing in the hands-on practice? Just type Y in the chat box if you are following, you are doing the experiments. Nandita, really nice, good. Anybody else? You are doing it? Look, Nitin, Yuvraj Singh, nice, very good. So I hope it will be very helpful for the students. LT Spice is the software which is especially good for the electrical or electronics engineer. But if you are from civil engineering or other engineering branches, you will feel like I should install CAD/CAM softwares and all. Instead of taking LT Spice, I should take it AutoCAD. So basically, it will create the problem, right? Because your device hangs on if multiple softwares are there. So this is the good way to make the students learn. What you can do, you can ask your students to go and perform on the virtual labs and give you the screenshots on this. So it is going to, maybe you can ask them to vary the resistance. For example, in the same thing, I will delete all the connections and I will be varying the resistance. So I will be looking that there is a little bit difference in this. So the same thing we'll be doing for the next one. Let us see. So I'm going to home. This is not home. I'm going to the list of experiments. So I'm deleting whatever was just after experiments. Go to the virtual labs. Basic electronics, list of experiments. Go to the list of experiments. So in order to help you, I am pasting the link in the chat box. So click on this. It is going to take you on the list of experiments for the basic electronics virtual laboratory. And let's do the full wave rectifier. Okay? And after that we will do the capacitive rectification. So this is the full wave rectifier. Go to the simulation. I am skipping the portion of theory and the procedures and all. You can go through that. If some issue is there, you can just get back to me. Full wave rectifier. So it is the bridge rectifier. We have studied this bridge rectifier in the morning class, right? There are two types of rectifiers. One is bridge and the center tap rectifier. So we have covered bridge rectifier, center tap you can take at your own. Okay. So in this, the same thing, what you have to do, first of all, click on the resistance because it is already drawn circle. Now click on button, make it the on button on. Now you can see the sine wave is active. So click on this. As soon as you are going to click on this sine wave, your oscilloscope becomes active. So click on oscilloscope and you will be able to see the output on the screen, right? Click on dual. So after clicking on dual, you can see there are two waveforms. One is the sine wave. So I am going to change the position so that you can visualize it in a good way. And let me modulate a little bit. Yeah. So now you can visualize that the input is this and output is this. This is the full wave rectifier. Okay, I was just checking something. So this is the full wave rectifier. The same thing we will be practicing with drawing the circuit. So click on the draw circuit, and now it is with you. You have to draw the circuit as per the instructions. So look at the instructions: L1, L7, connect both of these. L4, L2, L12, L5, L12, L11. So L1 and 7, L4, 7, 12, 5, ground. After that, it is 12, 11, 8, 9, channel 2 output, 6, 10, 3, 11, 10, 8, and then 10, the output connected to the oscilloscope. Check the connections, click on the check the connections. Yeah, connections are correct. Now you can see the RL is active now. So drag the RL, let's say 1 kilo. And now what you have to do, click on, make it on. So sine wave is now active. You can see the black color. Click on this sine wave. As soon as you are going to click on this sine wave, your oscilloscope, which is inactive right now, that will become a dark blue. It means that will become active. So you can see I have clicked on sine wave and this is active now. But I cannot see the output over here, right? So for that, I have to click on oscilloscope and output is going to appear on the screen. So I'm clicking on the oscilloscope and you can see the output is appearing on the screen. Now only the output waveform is going to appear. So for that, I have to make double click on the dual channel. Dual. So this is the dual button on the screen. You can see my cursor. This is the dual button. I'm just clicking on this. And it is going to give me both of the waveforms all together. Right? Both of the waveforms are available all together. So what I'm going to do is I will be dragging it by position. I am changing the volt per division by axis. And likewise, I'm going to change it for the output as well. 0.5. Let's make it similar so that we can visualize in a better way. Comparison will be best. Right? So in this manner, you can visualize it. Okay? Fine? So I hope you understood it. If you have any query regarding this, please type in the chat box. If you do not have any query, you may type any in the chat box so that we can proceed to the next experiment. If you have any query, please type in the chat box. If you do not have, just type N in the chat box so that we can proceed. No query. Okay, good. So now I am going back to the virtual labs and the list of experiments again. Go to the list of experiments and let me take the rectifier, capacitive rectification. So this capacitive rectification, we have already done it. So rectification for full wave rectifier, I'm going to take. Full wave rectifier, I'm going to take. I will just take this one. After that, we are going to do the LT spice simulations. So these are the instructions given. There are 4 diodes and you have to follow the click on and then click on the sine wave, run the simulation. So after let us make it again. So first of all, you have to click on this on button. I have taken just the first one, the simulation. If you want to repeat, I am going from here. This screen is going to appear, right? On this, the first one or the second one, whatever you will be having, capacitive rectification for full wave or half wave. The first one is the half wave rectifier, the second one is the full wave rectifier. So I clicked on the full wave rectifier. You can also click on half wave rectifier, right? What you have to do? First of all, click on button. So this is the on button. When you will be clicking on this, the input is active now. So once the half wave rectified, you are going to click. It is using that the capacitor is not available. So this is the actual half wave rectifier, which experiment we have already completed, right? Now what you have to do? Run the simulation to the capacitor. So click on this, and this is what the output as per the capacitive filter we are getting for the half wave. You can visualize on the screen. So if you want to see the input and output, then double click on the dual and you will be getting the input and output. Okay, so this is the input and this is the output. So likewise for the full wave rectifier also we can do. So the full wave rectifier, we have the circuit over here. I'm going to make it on. Just click on this on button. This is the on button, right? On the screen my cursor is moving. This is the on button. Click on this. This is the full wave rectifier, which is now active. The input waveform is active now, full wave rectifier. So basically, we'll click on this. This full wave rectifier, actually the input is taken just like your without capacitor full wave rectifier circuit was. So this is what your output you are looking like. Now this is also on run the simulation. So run the simulation when we are going to click, you can see that the output is appearing in this way. This the capacitor is going to discharge just after the half of the cycle. The input is more, then it is going to charge in this way. Double click on the dual and you are having such type of waveform. You can just change the positions. So you can see the positions over here. If you are going to change the positions on the y-axis, you are getting it in this way. Now you can visualize, right? You can also change the pitch in this way. How much amplitude you want, you can do it in this way. Change the y position. You may change the phase also. Frequency if you want to change. And similar to that. Okay? And in the calculations part, the ripple factor, form factor, all these things, all these calculations are given up. So what is the ripple factor and why it is used? Ripple factor is actually how much your output is being varied from the input average value. So that's going to tell you the ripples, the variations from the average value. It's going to tell you about the variations from the average value. That is your ripple factor. Okay. Then there is something called form factor. Form factor and ripple factor, both of these are correlated. And you have to find out the average value. That is nothing but the DC value. Average is just the indication over one time period, and you will be averaging that out. Then there is RMS value. Generally, that is also known as AC value. Right? RMS value is also known as AC value. Root mean square. What you have to do? First of all, you will be doing the square. You will be averaging it out over the time period, means 1 by t, and then root, under root of that you have to take. So that is root mean square value. Standard way to find out one value for the AC, so that the power dissipation of that AC is equivalent to whatever this much of DC was. So this is the meaning of root mean square value, that this particular AC will dissipate the power which this VRMS DC, if it was okay. So if you have any questions so far, please feel free to ask. Any questions so far? Any questions, please ask. If you have any questions, you please ask. Otherwise, let us do the experiments related to oscillators which were discussed today by Professor Gaurav Datta. On LT Spice, we will be doing the problems related to that, sorry, practice related to that. So, have you installed the LT Spice in your system? Any one of you? I know it is very busy schedule for the faculty members and researchers and the students as well. The reason being, many of you are having the exam duties. BTech students are having their own exams, and these people are actually faculty members have to give the exam duty, and they have to check the question papers, they have to make the result and all these things. So I'm really very thankful to all of you that you people are joining. You are taking out of your busy schedule, you are taking some time to learn something. And I really want that something you should take away from this FDP, so that you can further propagate that to people, to the students whom you are going to nurture. Those are upcoming engineers of our country. So that's what I just want, that it should be valuable input for you, those who are spending the time. So if you have any questions so far, please feel free to ask. Otherwise, I'll request Sanjay Bagaria. Mr. Sanjay Bagaria, please share the screen and let us start the simulations related to LT Spice.
Hello, am I audible? Yeah.
Yes, you're
Yes, yes.
audible.
Okay, thank you. Okay. So we will go with the simulation using the anti-spice for the or different oscillator circuits like morning you have sessions. So today we are going to simulate using the anti-spice, the RC phase shift oscillator, Hartley and some Colpit oscillator. That's for the high frequency. So the oscillators are the basic circuits which generates the output oscillations, not only the sinusoidal but also the square and the triangular waves, and without any external clock or some external input generation. So So we will going to simulate with the square sinusoidal oscillator. So the basic criteria for the oscillation is the basic two bar Hussein criteria, that the gain of the oscillator, that the A beta, that should be 1, and the output phase should be either 0 degree or 360 degree. So the oscillators will have some two kind of network, that is the gain and the feedback network, that is beta, and the feedback is being always being the positive feedback being used for the oscillation circuits. So for the RC phase shift network oscillator, that is being used for the low frequency applications and used for the audio ranges, that is being composed by the resistor and the capacitive network, and we can make the oscillator by using either BJT or op-amp. So we can make a three set of RC oscillator by making such kind of network, like RC of three network, and this each network will provide a phase shift of 60 degree, and we use the three networks. So by providing the three network, the phase shift of 180 degrees being achieved, and the necessary condition for the oscillation is being that either 0 or 360 degree. So the remaining 180 degree phase shift is being provided by the this amplifying network. So this network will provide the 180 degree phase shift, and for this will also provide the 180 degree phase shift of oscillator. So same, amplifier will provide 180 degree and RC network will provide the 180 degree, that's the Barkhausen criteria. And this is the frequency formula for this, that is the F is equal to 1 upon 2 pi root 6 RC, and the gain of that should be greater than 29 to compensate the decaying oscillations. So these are the circuit diagrams using the BJT network, that is the NPN transistor, and also we can simulate using the op-amp operational amplifier. So let's moving forward with this oscillation circuits. So I have made this circuit for you. We will do it again. Let, so, so this is the basic amplifier circuit. This is the BJT amplifier, and this is the feedback network. So let's make another circuit. Let's make a circuit. It is R. Now let's connect it. So as per this Barkhausen criteria, this RC network should provide the phase shift of 180 degree. Let me show you how this will provide you the 180 degree phase shift. Let's connect a voltage source just to demonstrate you that is this network is being providing a phase shift of 180 degree or not. And, make it as a sinusoidal oscillation. Let's say amplitude 1, frequency let's say 1K and make it as 0.01. So is this circuit clear to everyone? And we will run it. Let's say we will simulate it for the 5 milliseconds. So this one is the input waveform and this output. It's being decaying. So let me increase the output because it's a resistive network. So okay, let's. So you can see here, this there will be a phase shift of, that is the input and this is the output. So there is a phase shift of 180 degree between the input signal and the output signal. So this is just for the demonstration. Now we will make it a full-fledged amplifier circuit. So we can connect a transistor, let's say NPNs. I'm going to make it using the BJT, then we will demonstrate using the. So you can see this circuit I have simulated. This is the transistor. Let me show you the simulation circuit. So this will be the output waveform. You can see here. This is the output. Just change the color. So you can see. And this, you can see here output voltage, and this is the same output. Just take the output here. So this network is being the amplifying network, that is being what we have made it is a this A is the this circuit, this BJT amplifier, and this one is the resistive network, and the gain of this being set such that this self-biased BJT circuit will provide a gain that is greater than 29. So I have designed this of BJT such that this gain will be greater than 20. So is this thing clear to everyone, or should I need any more explanation, please? Can you please reply with the chat?
Please type Y in the chat box if it is clear. If it is not clear, you may type N in the chat box or the problem whatever you are facing.
Do you need some more explanation in this regard, or
please type Y in the chat box if it is clear to all of you.
Okay, let me go with the another example using the BJT network. Okay, let's do it now. So it will be more clear to everyone. It's a component, let's say op-amp. Now we will take an op-amp. Now make a voltage source to connect the power supply. So this will be the feedback resistance, this will be the input resistance, and this. Let's make a connection. And now we are going to make it feedback. This output is again being feedback to this input to make it a positive amplification. And this is being used. So okay, so the gain should be greater than 29. Let's say I'm making it as a 58k and it's being a 2k. So 58 by 2, that is a 29k, and make it a power supply, let's say 9 volt. R is being, let's say I am taking as a low value, let's say 205. All should be equal, and C should be say 0.7 nanofarad. Okay, so let's run the system. Then transient, let's say 0.5 millisecond I have to run this system. Okay, it's error unknown. Let's change the outcome. Okay. Okay, the reason is this power supply. So this system is being run. So let me decrease this simulation time sometime. Let's say 2. Let's say okay. So are you able to get it this visible this screen too? So this will be the output oscillators. Let's say. So we'll zoom in this and click here. Let's say double cursor. Then okay. Move to this here and this. Now we can see here the frequency is around, let's say 400, around 400 kilohertz. Okay, using this op-amp circuit. So, and we can also cross verify with this circuit. So this is 1 upon the gain of this circuit is that the 1 upon 2 pi that is RF upon R1. This R1 is the feedback resistance, and then this is the input R2. So the gain is open for this circuit is being defined as the, that is for this, this R that I have taken, it is a 52K, and this I have taken is a 2. So this is in the inverting configuration, that if the signal is like this, so the output will be like here, amplified. That is the 180-degree phase shift here and 180. Similarly for this network, if the input is here like in this phase, the output will be the out of this phase, and the remaining 180 degree is being provided by this network along with this. Okay, so this is the RF upon R1, that is for your 52/2, that is 29, we have got it. Okay, so let me make you at a cross verify. Let's verify this also. Okay, we have simulated the circuit. Let's say run the system, measure the output. Let's change the color so it will be more easy. Make it 2 cursor. So the first cursor will be peak here, and the second cursor will be peaking here, and the output frequency will be around 1.6 kilohertz. So let's make it cross verify by analytical formula, and the formula for this circuit is the 1/2 pi root 6 RC. So you can able to see here this formula we are going to see. Let's see, 1/2 pi root 6 R. The R we are going to use, it is a 3.3K. 3.3K, and the capacitor is 0.01 microfarad we are going to use. And using this analytical formula, I am getting it's around 1.9 kilohertz analytically calculated value. And using the simulation tools, I am getting it's around 1.6, nearly 1.6. So that's being the partial difference between the analytically calculated and the simulated value. That's by using this either changing the values by using either this input impedance of this circuit is being changing, or the parasitic capacitance is being introduced, or some frequency response of this BJT. This BJT is being used. So is this concept clear to everyone, or should I go with some another more examples? Please reply in the chat box. Do I need some more examples with the RC phase shift oscillator? Please. Okay. Okay. So should I proceed further? So this is the whole concept of RC phase shift oscillator. Now coming to this Hartley oscillator. So I am also use this Hartley oscillator by using this BJT only. So by reason for this, instead of using this R and C network, we will introduce the L and C network, that is the tank circuit, to make it a high frequency oscillations. So I will proceed with the another example for you, and the frequency F is being here, that is the F output is equal to 1/2 pi, that is root LC, and the L is the equivalent, that L equivalent is equal to L1 plus L2. So we are going to use two inductor circuit. Okay, so if you have any kind of doubt, you can just ask me at any time. Let's make another circuit. Let's take up BJT, which is NPN. Let's say it's a BJT. Again, we are going to make it using the cell bias circuit. So, connected. Okay. Now we are going to introduce two inductors here. So first inductor, that is L1 and L2 inductor, and a capacitor, that is the emitter bypass capacitor, and that is one is the output capacitor, and this is the oscillation tank circuit capacitor. And now connect to the circuit. So this part is the amplification part, and this is the feedback network. Okay. Complete the circuit. This is the output. Now I need a voltage source to make it a power. Make it a ground, and this in between is also need to be grounded. And let's say select a pick a transistor, and now this time I'm selecting this transistor. And supply voltage, let's say 12 volt. And RC, let's say 100 ohm. R1, let's say 1.2 k. R2, let's say 10 k. Then RE, let's say 1 k. And emitter bypass capacitor is, let's say 1 micro. And this is, let's say 2 nanofarad. And this, let's say 1 nanofarad. And I'm going to use it of, let's say 1.2 micro Henry, and this is 12 micro Henry. Okay, so the circuit completed. Let me run this system for 5 milliseconds, and then output. Okay, let me check with this coupled with the iron. Okay. That's the 2 nanofarad. This 1K, 10K, and 1.2K. Okay, we need to introduce one more capacitor. The input capacitor. Make it, let's say 1 micro. System is complete. Okay. Okay, it's very loud. Okay, again we could reduce, let's say 10 micro. No, make it as a 20 micro. Okay, so this will be the output of this stable output, and this the initial part is being the settling time. It has color change to cursor. Okay, so the first cursor and the second cursor, and the output frequency is around let's say 1.2 megahertz. And let's make it as a cross verify by using the analytical formula. Let me 1 upon the formula is this is the 1 upon 2 pi root L1 L2 and C. So what we have used this value here, here, and the L1 L2, that is the 12 plus 1, that is the 13.2, and this is 1 nanofarad. So make it as a, okay, so remove this 13 microfarad, that is 10 to the power minus 6. And this again, that is value is 1 nanofarad. So 1 10 to the power 1 nano. Okay, is this thing clear? Okay, this is not okay. Okay. 1 upon 2 pi. Okay. 13.2, that is L1 to 13.2. 13.2 microhenry and then 1 nanofarad. Let's say how much it will be give. It's in megahertz, no? So, it's giving 1.3. 1.3 we are getting analytically and 1.2 by theoretically. So for this circuit, let's say we get it around 1.3 megahertz, and using LT spice we get how much value we get? This LT spice we are also getting 1.7 megahertz. So is this thing clear to everyone, or you need some more explanation? Kindly reply me in the chat box. Kindly please reply me in the chat box, or any questions, doubt. Should I proceed with this, or do you need some any more explanation or more example circuits? Am I audible, or please say something?
Yes, please type in the chat box if you have any query so far.
Should I proceed with the same pace, or slow down my pace, or increase, or include some more example circuit? Please reply.
Please reply in the chat box.
I have shown this by using this analytical.
Are you able to understand at the same pace? Type Y in the chat box if so. Otherwise, type N in the chat box.
I have make it is a comparative analysis for using the LT-SPICE output and the formula which we have derived analytically using the conventional mathematics. So this will be the amplifier circuit and this will be the feedback network. So there is no compulsion that we need to design the circuit by using BJT only. We can make it as an operational amplifier, or using MOSFET also. We can design amplifier using number of circuits. So proceeding further, this will be the Hartley oscillator. Let me make it as a comparative. Why we are going to comparison? This RC phase shift is being used in the range of low audio frequency range. That is something around in the range of kilohertz. And these two oscillators, that is the Hartley and the Colpit oscillators, being used in the range of something like radio frequency, that's the range of in the megahertz range. So with these two, along with this RC phase shifter, there will be the another oscillator, that is the Wien bridge oscillator, also that is also in the range of audio ranges, because these two network R and C will generate the frequency in the range of kilohertz, and using this tank circuit L and C, that is the basic tank circuit of L and C part, we are going to introduce, that mostly the frequency of oscillations will be the that omega will be root LC. That is the for mostly all the circuits, that the omega of frequency of oscillations will be root LC. Okay, so let me introduce by another examples. Let's say Colpit circuit also. Let's make another circuit, Colpit oscillator. Okay, let's make a new circuit. Should I go with the another, or let me modify this circuit also? Okay. This is the Hartley. Or should I make this another circuit? Let's say introduce NPN transistor. Next is the NPN transistor. Make it as well in the cell bias circuit. Introduce an inductor. And the capacitors. So this is the tank circuit we are going to make. This L and C are parallel, and we have to make it as a ground, and this will be our output part. And this is the feedback part. Okay. Now we have to excite it by the voltage source, power supply, ground. Okay. Let's say power supply will be the 12 volt. Again, we need to pick a transistor, and I am going to pick it as a there same BC 547 transistor. Let me make it as a 3K. So you need the BJT self bias circuit designing, and the H parameter modeling, and using this either RE model or pi model to design the BJT, so that we can design the amplifier, that how much will be the gain of this self bias circuit using this circuit, and after that we will introduce the feedback network. So the initial prerequisite is for the designing, either using the operational amplifier or the BJT circuit designing is being required to make a oscillation circuit. Let's complete it with this. Make it as a 3K, and make it as a, let's say, 10K, and make it as a 50 ohm. So let's say 1K. And bypass capacitor, I am introducing it as a 1 microfarad. And this input capacitor is 1 micro, and this oscillation capacitor I am going to using as a 47 nanofarad, and it's a 20 nanofarad. Okay, is this anything left? Okay, okay. Now run the system. Let's say I'm the 10 microsecond. Okay, L1 is not defined. Okay, so make L1 is 2 microhenry. And then run the system, plot the output. Okay, it's not been concluded. Make it, let's say it's a 30 micro. And this is being also introduced. Let's change the color. Blue. Make it as a 2 cursor. Okay. Make it as a 1. And let's say I'm going to magnify this to 2 cursor. Okay. I'm modulating the cursor. Okay. Let's again simulate. Take the output, magnify. I'm going to do this. Click right, change the color to cursor. Okay, no, this is the first cursor at the first peak, and the another cursor at the another peak. And the output frequency is being around that's 950 kilohertz, so it's almost 1 megahertz is being ranged. And let's make it as a cross verify using this analytical formula. And for this, the frequency formula is being same 1 upon 2 pi root LC, and the L is being equivalent capacitor. That the when we introduce the capacitor in parallelly, we are going to introduce some capacitor. Let's say this is the C1 and this is the C2. So the equivalent capacitor is in the C1, C2 upon C1 plus C2. This is not reversed by the case of resistive network. So this will mean the C equivalent. It is the C equivalent capacitor and L. So what we have used here, so C is equal to 47 plus 20 nanofarad, and L is 20 47 plus 20. So that's it. So this is been 47 nanofarad, this is been 20 nano, and this L is 2 microhenry. So let's make the capacitor equivalent. So can somebody reply me the equivalent frequency analytically in the chat box? So there will be not a one-way communication. Can you please reply in the chat box that how much frequency we are going to get with using this formula? Just put it the C. Just put the C is equal 1 is equal to 47 nano, C2 is equal to 20 nano, and then L is equal to 2 micro. Let me calculate it for you in this calculator. Okay, that's C1 into C2. So 20 nano, 47, 20 nano. So 47 into 20 upon, that is, sorry, 767. So it's around 14.03 nanofarad C equivalent, and L is equal to 2 micro. Okay, so let me 2 micro and 14.03. 14 nanofarad. It is in 2 micro and it is 14 nano. So how much frequency we are getting? That's the same. That is the for 950 kilohertz and analytically. So let me show. Yes, for this circuit, we are getting the same frequency, that is the 960 or 950, and we are getting here. So, is this concept clear to everyone, or do you need some more explanation or some more examples I need to produce? Please reply in the chat box. Am I doing some mistake analytically, or did you guys get the same value what I have got, or you are using the in by a hands-on session by hand in hand, or facing any problem? Please reply me. So it should not be a one-way communication. Anyone please reply, or am I audible? Someone please reply. Anyone? That do you need any more explanation in this regard? Should I go with another example or should conclude this session here? Are you guys am I audible? Please, guys, please reply in the chat box. Okay, 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 got it, got it. Oh, should I conclude the session or go by another more examples using OPAM or? So basically, you need to design the circuit, designing circuit or using the this condition that let me here. So these are some designing point of that we need, that how we are getting this 29, and for this 29 that you need to select the parameters. So guys, what we are talking is that this 29, how we are getting the 29. So for this 29, we need to design the value of R1, RC, that is the RE emitter, unbypassed capacitor, that's CE, that is the bypass capacitor, and the transistor, that is the important part that we need to define using the beta, that is HFE. That is the current gain of this amplifier. So for this designing the oscillator, you need to, the prerequisite is there to design the BJT amplifier, and also for using this op-amp. Using this circuit, and similarly for the Hartley and the Colpit oscillators also. So This is the amplifier circuit using the op-amp, the gain. This is the basic op-amp circuit, uh, that is the RF circuit and the R1 circuit. And by using the applying the input, that is the minus sign, that means the inverting input, that is the inverting input, and this is in the non-inverting input. And so the gain of this inverting input is being there, that's the one that is the minus RF upon R1, that is the gain, that is V output upon V input. And this minus sign signifies that the output phase is 180 degree, that is the phase shift between input and output is 180 degree. Similarly, if we apply the input to the positive phase, so the input phase and the output phase of this op-amp is in the same, there will be no phase shift. But initially what we have started here, this Bar-Hussein criteria, that is the two conditions, that is the output phase should be 0 degree or 360 degree, and the another one criteria is the A beta should be 1. So there will be designing all this circuit. So for this circuit, we need to introduce 180 phase shift by this and the 180 phase shift by this circuit also. Similarly, for this common emitter amplifier, the emitter amplifier will provide the 180 degree phase shift. If you are getting the output directly from the emitter, that is in the common collector configuration, there will be no phase shift. Like if the input is being this, here the output will be in this circuit. So that configuration is not being possible for this RC phase shift oscillator. So we need to take care of this, the designing part. So in this session, we are only concluding with the designing of this feedback network, then concluding. So I have make it possible to show by using this analytically as well as design using the LT spice circuit. So you guys just try with this all the circuits, what examples I have showing the demonstration, and if you face any kind of issues, you just connect me or the mem, will help you or will create another session on the or doubt or some you need and some more example circuit, will do it. So let me check the chat box if you guys are facing. Okay. Screen not visible. Screen not visible. Okay, I'm not sure. Okay. Let me check with this. Okay, sorry guys, sorry I didn't check. So I am explaining all these things, just that the Bar-Hussein criteria which we have seen, that is the two necessary conditions which being there, that the A beta should be 1 and the output phase it should be 0 or 360 degree. The output phase should be 0 or 360 degree. So in the op-amp circuit, the minus sign is being applied. So this minus sign is the inverting input, and this positive sign is being the non-inverting input. And for this, the gain formula is being there, that is the minus RF upon R1. And this minus sign signifies that the phase of 180 degree, and this remaining phase is being provided by this RC network. Okay, so for this, the necessary condition should be 1 upon 29 that we have derived analytically in the morning sessions. So for this, we have introduced this designing using the op-amp. So not this op-amp. This is the op-amp circuit. So you just guys check, that is the 52 upon 2K. That is the 52 upon 2K. That is here I am designing by using the 2K. That's the 29. And this circuit will check the frequency of the circuit. Can we show this, how much frequency we are getting? Let me check. Just introduce the capacitor. One is here and the double cursor. Okay, now the one cursor is being here, the another cursor is being here, and I am getting it's around, let's say, 400 kilohertz. 400 kilohertz. Let me verify it by analytically that. Okay, so where is my calculator? Okay, this is my calculator, and next 1.25 root 6 into RC. R is my, for not for this circuit, this is for, okay, this is my circuit. From this R is equal to 205, let's say 205, and my C is equal to 0.7 nano, so 0.7 nano, 10 to power minus 9. Okay, 10 to power minus 9. Okay. Okay. So what will be my frequency? It's around 450 kilohertz, and what I am getting by analytically, let's check here again. Two cursor. Okay. Now one is here, another one is here, and it's around 400 kilohertz, and I am getting it's here 450 kilohertz. 450 kilohertz, है ना? So guys, there will be a 450, the difference of 50 kilohertz, 50 kilohertz. So what will be the reason? The reason will be the choosing the op-amp characteristics. That is it the 450 of it being the pass band frequency range of this circuit, or the some power supply consumption, or there will be a shift in change in this input impedance circuit. So there will be some minor mismatch between the analytically derived formula frequency and the simulated frequency. Okay, so the frequency which we have derived using the analytical formula, that is purely analytically without considering into the designing component being used. Either we are using with the operational amplifier or the BJT, or if the BJT, it will be the NPN or a PNP kind of transistor. So ignoring all these things, we have designed the analytically formula, and in the practical simulation LT-Spice, we have just introduced the amplification component, that is the A part, by using either it will be a any amplifier. You can design by using the MOSFET also. So let me check the chat box here. Any okay, screen is visible. Okay, okay. So okay, got it. So guys, should we conclude this session, or any improvement or any things this session interesting, or do you need some more? Please reply.
Yes, any input from the audience, if you have, please share. Any query or anything else related to it? Please type N in the chat box if you don't have any query. Please type N. I hope I'm audible to all of you.
Okay, so we may conclude some more session if you required, or some more example circuits for this. Today I have just introduced the three oscillator circuits. The first one is the RC phase shift, and the Hartley and the Colpit oscillator, that is for the high frequency oscillations. We can design either using the MOSFET also, and the WinBs also remaining. You can try yourself, and if you are facing that, let me know. We'll conclude the session. Or you just do by yourself this the same circuit which I have designed. Just do by your own hands-on session on your laptop or personal ground system. And if you are facing some issues, please let me know. I will help you with this session.
Okay, thank you, Mr. Sanjay, for the valuable insights about LT-Spice, and you have taken really good and explanatory session on the both of the days, which was hands-on session on the LT-Spice. You have covered a lot of examples. I hope all the audience will get benefited out of it, and all the faculty members who are, they will be able to train their students on these type of softwares so that the students can learn more, because the experiential learning is the one thing with the help of which we can register in the memory of the students forever. Thank you so much. Format of the quiz. So format of the quiz will be an MCQ type or one word type of quiz, and let us have tomorrow evening after